Well, hello, everyone. My name is Jeff Kodosky, co-founder and fellow at NI, also known as the father of Lab. Well, I would like to thank the organizers of this online summit for the opportunity to present today. This is a new experience for most of us, I'm sure. It's the first time for me presenting virtually, and so this will be a bit of an adventure. So by way of background, in recent years, I've been focused on how we can do more with LabVIEW, but spend less effort doing it. I've presented on a number of ideas multiple times, but this is the first time I've organized my thoughts on frameworks for presentation. So what are frameworks and why do we create them? Well, a framework provides common infrastructure, so it doesn't have to be created from scratch and debugged over and over again. This speeds development, reduces debugging, and lowers the risk in creating a successful application. You can view a framework as reducing artificial complexity. An application has inherent complexity of the job to be done and the artificial complexity of the tools being used. A framework is a more powerful tool which reduces the artificial complexity and overall complexity of your application. Using a framework is like hiking on trails maintained by the Park Service, as opposed to blazing your own trail through the forest. You can hike many more trails when you don't have to clear them all yourself. And although you're constrained to hiking on trails, you're likely to have safer and more enjoyable hikes. Frameworks are similarly constraining. They constrain the allowable designs you can make, but the result is a more analyzable and maintainable application, and one that can be more easily replicated and modified. Applications that have concurrently executing parts can be very challenging to create and debug, and this is where frameworks are particularly helpful. And while frameworks in LabVIEW are certainly helpful, I've always felt they illustrated a shortcoming. If they are allowing you to work at a higher level of abstraction, why can't that higher level exist as a native capability? Why can't LabVIEW embody the framework natively? We build a framework out of the basic features in LabVIEW, but its operation is often not so easy to understand. And it often isn't protected and enforced in the LabVIEW environment. One of the earliest frameworks is the queued message handler, which is basically a concurrent producer-consumer application pattern. The producer is a loop, typically with an event structure, which sends messages to the consumer or in a message handling loop, which is where the principal functions of the application are located. So why is this a framework? Well, it's implemented using references that have to be initialized, passed to each loop, and cleaned up afterwards. And using references is more complicated than typical data flow. So having a robust and debugged framework saves time and increases the likelihood of success. You create your application by putting your specific code into the designated locations, indicated by blue comments here, leaving the rest of the infrastructure alone. While this framework definitely helps, it isn't as simple to understand as the phrase producer-consumer might imply. The issue of communicating concurrent loops has nagged me ever since LabVIEW 1, and it's especially concerning since it's so easy to create parallel loops in LabVIEW. Well, to make a long story short, after a decade of prototyping and experimentation, we introduced channels in LabVIEW 2016. Using channels, it's much easier to understand and to create producer-consumer applications. I claim that channels represent a higher level of abstraction. In essence, a native implementation of a framework element. For those of you unfamiliar with channels, they are now being taught in the LabVIEW Basics class, and you can find a variety of interesting examples in the Examples Channels directory. I've given a number of presentations on channels in the past, and some of them are recorded and even available online. The presentation of a channel looks like a pipe because it's different from a normal LabVIEW wire. Nodes connected by a channel imply concurrent execution, as opposed to sequential execution if they were connected by a normal wire. I haven't convinced everyone to use channels yet, and the reluctance of some LabVIEW users is understandable. I know for myself, if I'm proficient at one way of doing something, I'm reluctant to adopt a new way, even if ultimately it's easier. Still, it would be good to see more adoption of channels in the community so we could continue to advance the state of the art in graphical programming. For the remainder of this presentation, I will assume familiarity with the basics of channels and build on the concept. As a quick review, here are the main kinds of channels in LabVIEW today. Stream is typically for homogeneous data with queue semantics for a single producer and a single consumer. The stream channel also has a sideband, which facilitates orderly shutdown. There are also several specialized and optimized versions of stream that exist as well. Tag is for sharing any kind of data where no history is needed, only the latest value. It's like a scoped global with multiple readers and writers. One common use case, a simple use case, is shutting down multiple otherwise independent loops. Messenger is typically for structured data messages or objects. It has queue semantics, but supports multiple readers and writers. A specialized version of Manager exists where the messages can be sent to an event structure. There are still situations where people find it necessary to use references and pass them around their application. And this suggests to me that there's opportunity for more abstractions. We just need to exercise our imaginations to conceive of them. A couple of years ago, I was inspired by an application that Bob Shore created using channels and the challenges he faced doing it. The application consists of a main controller and multiple independent experiment stations, sort of a manager-minion arrangement. The manager communicates with each minion individually and is responsible for their overall coordination. The minions only communicate back to the manager, not with each other. Another complementary structure is multiple independent clients communicating with a server. So these and other examples could probably benefit from additional abstractions. I continue to experiment with more kinds of channels to address a broader range of application patterns. And one that is particularly promising is what I call the multiplex messenger or MessengerM channel. It's a channel that represents multiple messenger subchannels. The subchannels can be accessed by index or unique name. MessengerM was inspired by the manager minion pattern, but I've recently realized that with an extra tweak, it even has wider applicability. And that has gotten me thinking more about frameworks. So to complete the description of MessengerM, it has the usual read and write endpoints, but there's an extra input to specify the particular subchannel to write to or read from. There are two more pairs of endpoints that use a unique name to identify the subchannel. Why these extra endpoints? Well, since manager channels support multiple readers and writers, the MessengerM channel can actually support bidirectional communication. These extra endpoints facilitate a call return style communication between concurrent loops. The caller sends a message which the callee reads, and then the callee sends a reply which the caller reads, all on the same bidirectional channel. I'm still exploring various ways the MessengerM channel can be used, but I think it represents another abstraction that helps implement frameworks natively. The actor framework that ships with LabVIEW is another robust framework. It's a powerful tool, but it's not so simple to visualize and understand an application built using it. So I've been thinking about how to make an actor framework application more easily visible, and I've dubbed my idea the Visible Actor Framework. The idea is to make the actors and the communication paths between them explicit. An actor is basically a concurrent asynchronous process, and there's no loss in generality, representing a simple one as a while loop. A more complex actor can be represented as a group of nested communicating actors. If every actor communicated directly with all the others, this would be a nightmare to understand, analyze, and debug. The actor framework imposes some structure on the communication paths. In particular, a recursive manager-minion structure. This is much easier to understand and create, and it's not too constraining, so it can be applied very broadly. An actor has a single input and a single output. The output goes back to its owner. A composite actor has a message port going to each minion or nested actor. Communication is typically constrained to go between manager and minion only, and not from minion to minion. This makes designs more modular and easier to understand. The minion's output messages merge into the owner's input port, which simplifies message processing and reduces race conditions. An actor starts up and shuts down its nested actors, either statically or this can happen dynamically at runtime. A nested actor can also have its own sub-nested actors, but these aren't directly accessible to its owner. So what follows is a storyboard for editor enhancements in LabVIEW, which could natively implement an actor framework that enforces these communication constraints. A variety of things figure into this storyboard, and you may not be familiar with some of them, so let me briefly describe them. The first is scripting. There are functions in LabVIEW which you can drop on your diagram so that at runtime, it will create and edit a new VI. In other words, you can make a VI that can automatically create other VIs. This is an extremely powerful feature that is the basis of many extensions to the LabVIEW environment. It's not easy to use, but it does allow you to extend LabVIEW without having to be on the LabVIEW development team. Another feature in LabVIEW is the right-click pop-up menu plugin. This feature extends the editor by making it possible to add an item to a pop-up menu. You can specify which objects get the menu item, and you can use scripting to edit the diagram when the item is selected. I should point out that channels are implemented using scripting and the right-click pop-up menu extensions. This makes it very efficient to iteratively develop and experiment with new channels. The state diagram editor was a toolkit many years ago, but then it was discontinued. A few years ago, I met some folks who, like me, continue to see value in using it. So it's now resurrected as a feature in LabVIEW. You just need to know how to put the icon on the palette. It works by letting you edit a state diagram in a separate window. And using scripting, it creates and edits a case structure inside a while loop to implement it. The case structure, while loop, and transition logic are all locked, so they always match what's shown in the state diagram. You add your application logic inside the cases, but the only way you modify transitions is by editing the state diagram itself. The state diagram editor is an example of an external editor plugin. It's just a library of VIs, which means people can make other external editor plugins if desired. Again, because of scripting, it's not easy, but it is a way to extend LabVIEW's capability without having everything built in LabVIEW. Okay, so here's the storyboard for a visible actor framework. Imagine you could pop up to drop an actor. This might be made as another external editor plugin and be on the palette just like the state diagram editor. After selecting the actor, you drag a box just as you do for any other structure you want to create. And then the basic boilerplate for an actor is scripted, ready for you to add your application-specific code. The basic structure of the actor is locked in order to constrain how it can be edited. In this storyboard markup, I'm just showing a trivial loop as placeholder code. But later on, I'm going to have more to say about this because I think a real actor can start with a more interesting template. Note that the actor has a single input message channel and a single output message channel. Edits to the actor topology are made using a pop-up menu plugin, and they preserve the framework constraints. Pop up on the actor frame to add a nested actor. The nested actor is added and connected according to the framework requirements. That is, the nested actor's output message channel is connected back to the owner's input channel. A lock on the channels enforces the framework constraints. You can't directly edit the messenger channels. You can only add or delete actors. You can pop up on the actor frame to add another nested actor. Each nested actor is identified by a unique index, which is also locked. That's the meaning of the 2 and the 1, the so-called minion index for the nested actors. Manager to minion communication uses the multiplex messenger channel that I talked about earlier as a bus to connect the manager to all the nested actors. Each actor listens for messages on a specific subchannel given by its minion index. The filtering node makes sure that only the messages intended for the particular nested actor are passed through to it. Messages back to the owner are merged into the owner's input channel. If it's necessary to identify the particular nested actor that sent the message, if the manager isn't able to know that automatically, the minion index could be included in the message. That's what I'm showing here. You can pop up on a nested actors frame to create a doubly nested actor. Again, the pop-up does the scripting and locks the communication paths to ensure that the framework invariant, communication invariant, is maintained. So this diagram can grow fairly large. Instead of showing all the nesting and sub-nesting on one diagram, you could pop up to shrink an actor to a sub-VI, just like we do for create sub-VI from selection. Shrinking an actor to a sub-VI is effectively like zooming out to a higher level of abstraction. Note that the actor sub-VIs all have the same connector pane, a messenger input channel, messenger output channel, and a minion index. It would be great to be able to shrink and expand an actor and have the diagram smoothly adjust automatically, but that's still a futuristic concept. Everything else I've shown so far, though, is possible to do in LabVIEW now by using scripting and pop-up menu plugins. I can also further envision reducing the clutter of the infrastructure in these diagrams. For instance, docking the index to the minion icon. This could be done even now. It would just take a little more scripting effort. Applications that need to dynamically create and connect new actors could pop up to add an actor spawning actor. This is another actor with the same connectivity, but it's capable of spawning additional actors. By convention, the spawner uses channel 0 to receive a spawn message and starts up a new asynchronous actor. The ability to dynamically spawn a new actor makes it possible to create highly dynamic applications that still adhere to the framework constraints. Every actor that is spawned is given a new minion index and connects in the same way to the communication network. The runtime addition of a new actor follows the same conventions as the edit time addition. If we pop up and shrink the manager loop, we effectively zoom out and see the connection to the minions more easily. Shrink the spawning actor, and what remains is the high-level structure of the application. Just the actors and the communication paths, with the infrastructure completely abstracted. These are the actors that exist at the start of your application. But if more are dynamically added at runtime, they aren't visible, of course, and that makes it a little bit obscure, perhaps, for highly dynamic applications. However, if we had the concept of a dynamic diagram that could show new actors as they were created at runtime, that would be awesome, it'd be incredible. It would enable unprecedented visibility and debugging of dynamic applications. You could pop up to see the actors, you could probe the messenger channels to see the data going to the actors. This would be an incredible advantage for debugging, creating and debugging dynamic applications. So this is an extremely intriguing idea, but at this point, it's still super futuristic. So the previous storyboard slides represented actors by using a trivial while loop so that we could focus basically on the communication paths. But an actor template would typically be a lot more substantial, I think. Here, I imagine the actor template would actually be a state machine. Maybe it starts out with a basic 5-state model: init, active, error, exiting, and a terminal state which exits the loop. For illustration, I'm showing what could happen when doing a normal shutdown. When the actor receives the exit command from its owner, it tells its minions to exit and then transitions to the exiting state. When the actor notices all of its minions have exited, the actor can report to its owner that it has exited. The actor state diagram could be edited using the state diagram editor to add more capability or to simplify it, for example, if the actor has no minions. As usual, you can't edit the case structure directly, but you can edit the contents of the cases. That's where your application goes. Each case contains the application-specific code for the state it's implementing. I think the state diagram editor still shows too much locked infrastructure detail, and in the future, I hope this can be further abstracted. Well, that's my idea for a visible actor framework. And I think The storyboard shows a plausible native implementation of a framework. I can imagine still more that could be done to raise the level of abstraction and reduce the infrastructure clutter on the diagram, but maybe what I've shown in this storyboard could already be useful. As a final comment, let me point out that the active framework that ships with LabVIEW has a lot of object-oriented capability, which I have not attempted to represent in my storyboard. That will be something to consider in the future. So thank you all for your attention and enjoy the rest of the summit. Now with the help of the moderator, I can take some questions as time permits. I will also have a session after this where I'll have my office hours, if you will, and hang out for an hour or so in case anyone would like to discuss some of these ideas or other things in more detail. Thanks again.
All right, great. Thank you, Jeff. I guess we can open up the floor to a couple more questions. Seen just a few coming through the chat. So Hope Harrison asked, how would this type of framework handle if you want to inherit functionality from another actor?
So I can't hear anything other than you, Sarah, so I'm hoping that...
Sure, so Hope asked, how would this type of framework handle if you wanted to inherit functionality from another actor in your actor?
So right now, I don't have any of those object-oriented capabilities. So there isn't a mechanism for inheriting. If you need another actor, which is similar to another one, that you basically have to copy it and share in SubVIs the common code. The actor framework on that ships with LabVIEW has an edit time inheritance mechanism, which allows you to have one actor that inherits capability from another. It copies code to do it as well, but at least it has that inheritance connection. I haven't tried to explore that part yet.
Okay, great. I don't see a lot of other questions coming in. They have some real-time questions they want to ask. Otherwise, we can move discussion over to the office hours and then you can interact more directly one-to-one.
Yeah, okay, that sounds good. I guess I'll take a 5-minute break and then appear in the sessions window.
All right, great. Well, thank you so much, Jeff. There's a lot of really positive feedback in the chat. People seem to be very excited about the direction this is going in. So thanks, everyone.
Okay, thank you. See you in a few minutes.